Welcome back to module 5 of object oriented analysis and design. We have been discussing about the role of decomposition in modeling and solving complex system design problems, and we just briefly took a note of the algorithmic decomposition approach and the object oriented decomposition approach. And in the object oriented decomposition approach, we have noted that there will be a set of autonomous agents typically called objects, which can pass messages between themselves. So that whenever a object sends a message to another object, the sending object is typically called the client and the receiving object is called the server, and the receiving object will provide the service that the sending object has asked for. And that is the basic client server model on which the object oriented decomposition is structured. Now, let us quickly take a look into how do these two decomposition approaches compare. It is basically this, if you look into the history of what different design methods have been followed, there have been naturally tens of them, if not hundreds of them. But the most dominant ones have been the top down structured design, where you start from the most complex system as a whole and then you start breaking it down. This has been the basic approach of decomposition from a very long time, oldest and certainly the most traditional. But certainly this top down approach is closest to the algorithmic decomposition. It does not address issues of data abstraction, it does not deal with concurrency, it naturally does not scale up well with the extremely complex system. It is understandable because this has been very old approach, and therefore, in those old days the system capacity itself was very limited. So, the hardware capacity itself was very limited. So, all that you needed to do is to divide the problem to the extent that the hardware can handle. And also there is no question of handling concurrency, because there was always just one single processor executing everything. So, this approach primarily went on for quite some time, and it still is predominant in many with many of our designers and many of the design areas, and needs to be understood. But for the broad community of object based and object oriented languages, programming languages and paradigms, this is kind of become obsolete. Next, what happened is primarily data driven design, which kind of dominated the 70s and the 80s, where a typical characteristic of a data driven design is there is a mapping between the input system inputs and the system outputs, and this mapping can directly derive the structure of the software system. So, data driven design significantly had a fallout in terms of variety of information management systems, those which have been significantly based on variety of database systems and so on. But naturally they are not very good in terms of or effective in terms of time critical events, time critical systems. So, just to give you glimpses, a data driven design system would still be workable today for say a railway reservation, where though you have time bounds, there is not much of time criticality on whole of that. But a data driven design method would be disastrous if you are designing the braking system of a car, which has very critical time constraints and very complex processes to follow to honor those time constraints. And what has evolved over the last significantly over the last 20 years and emphasized over the last 15 years more are object oriented design methods, where you view the whole world universe as a collection of cooperating objects or autonomous agents, as I mentioned earlier, and you treat individual objects and instances of some common behavior classes, and naturally that is what is our interest of study in this course, and several languages including C++ and Java support that. So, keeping those in mind, we can do a quick comparison between algorithmic and object oriented decomposition. if we look into point wise, then algorithmic approach is primarily based on ordering of events, because it's primarily encoding of algorithm, that is the time order, whereas object oriented systems are more distributed. They emphasize on the agents that are clients and servers. Naturally, algorithmic decomposition leads typically to larger systems. Object oriented decomposition gives you smaller systems, because you can make better reuse of common mechanisms, better reuse of common properties. Leading from this is algorithmic systems get less resilient, or in other terms object oriented systems are more resilient, because since you can follow the stable intermediate forms that we had talked about. The stable intermediate forms are transitions of from a simple system to a less simple system to a more complex system to more and more complex system. So, you build the system over iterative refinement, and at every stage you have an object based view of the whole world, which may not be the exact view that you want, is a simplification of that, but it is still complete in the whole of the stuff, and therefore, can give you a correct system, which indicate that you have a much better resilience in terms of these stable intermediate forms, and it can reduce the risk by providing iterative refinement in the design process. Similarly, algorithmic decomposition is flat, because you are going task wise, whereas object oriented decomposition can clearly take the separation of concerns. I hope you recall what separation of concern is. Separation of concern is that any subsystem can be viewed as an independent one, and with a lot of intra-system traffic, with a lot of intra-system activities happening, and limited number of inter-system activities happening. And now, you will understand this inter-system activities are basically the messages that are going between different objects, and intra-system activities are also messages going between the constituent objects of the given subsystem that we are building. So, separation of concern basically gives a big advantage in terms of building such systems. In terms of computing model, we have seen that object oriented decomposition would use some kind of a client server model, which is inherently distributed, has a high concurrency, and therefore, in a large number of aspects object oriented decomposition has a really good benefit. But before we move on, just one word of caution, please do not think that algorithmic decomposition is useless. After you have come to a certain level of relative primitive in the object oriented decomposition, you will still need algorithmic decomposition to actually implement different logic, actually model different logic that your system may have. There are systems, there are complex systems which may be very strictly mathematical, formula oriented, where even though it is possible to do object oriented decomposition, your algorithmic decomposition may be a much more direct and easily realizable approach. So, it is gross observation that object oriented decomposition will have a lot of advantages, but you should always remain open in terms of starting with the one decomposition approach, and at every stage evaluating, considering as to which approach you should adopt and up to which depth. In general, any design of a complex software system will at different stages have some bit of hybrid approach, some bit of combination between the algorithmic as well as the object oriented decomposition approaches. Moving on to the other properties of complex systems that we can leverage. Certainly, the next property beyond decomposition is abstraction, and we have seen that abstraction is we have seen that there is a huge amount of disorganized complexity in the whole problem domain, arising primarily due to limitations of human brain, both the limitation of storage, the short term memory is small, typically 7 chunks of item, give and take 1, 2, and the speed is also limited. It takes a whole lot of time to process new chunk of information, irrespective of what that chunk is. These are all psychologically proven data that you can use, And therefore, to address the disorganized complexity, only major tool that we have in hand is abstraction, which basically what it says that just look into what you need to look into, what is of interest, do not look into the rest, do not look into the details. Always handle it by chunking. Chunking basically means dividing into small pieces, small meaningful pieces. Always handle information by the chunking process. So, here just as a side one, I give an example of chunking. Suppose you are given to remember this binary number, and I am sure many of you are young and have sharp memory, but you will still have a little bit of issue remembering them. But suppose I chunk them into 3 bits together. This is the same string. I just chunked it into 3 bits together, and then consider these as hexadecimal numbers. So, I got 6251. This is certainly a much easier abstraction to remember, or I could actually chunk them into 4 bits together and represent a hexadecimal representation of CA9. So, this is difficult to comprehend, this is easy to comprehend, this is easy to remember. So, abstraction is this is one example of chunking and abstraction, that is, you are trying to reducing the semantic load of the information that inherently exists, and the role of abstraction in different ways that it will play is to continue to reduce this kind of a semantic load. Finally, the design process benefit a lot from the role of hierarchy. We have already seen different hierarchies in the canonical form, and again it can increase the semantic content of individual chunks by explicitly recognizing the hierarchy structures, and we have already observed that we have already noted that 2 major hierarchy structures are part of the canonical form, the object structure, which show how different objects collaborate, and the class structure, which show what is common between different structures and behaviors within a system. So, these 3, the decomposition, abstraction and hierarchy, become the main tool, the main weapon, so to say, to win the war against the complex design of complex systems. And from the next module onwards, when we start discussing about specific design concepts, the notions, the languages and so on, you will see that we will keep on using a mix of decomposition, abstraction and hierarchy in different ways to actually solve the modeling and design problems. Now, before I close this module, I would just like to sensitize you about 2 things. One is I have been and will continue to talk about design, and so I just wanted to formally define what design will mean in the cases that we are dealing with. This is the meaning which is possibly common for almost all engineering designs. So, for us a design will have these basic properties and or rather attributes of concern. One is a design will have a functional specification, that is, it is for building some system which meet certain functional requirements, otherwise we are not doing a design. The second is it will need to conform to the limitations of the target medium, which means that I can take a functional specification and start doing a design assuming infinite amount of computing power or infinite amount of memory or infinite amount of network bandwidth and so on and so forth. That is not realistic. What is realistic is, on one side I have the functional requirements of what needs to be achieved by building this system. On the other side, there is limitations of what kind of processor, what kind of architecture, what kind of network connectivity, what kind of storage, what kind of bandwidth, and all these are available for realizing that system. So, that is the question of target medium. The third, it must meet implicit or explicit requirements of performance and resource usage. I can say that theoretically any algorithm can be implemented on any system, even if it has a couple of bytes of memory, but that is not what will give you a working system, that is not what will give you working design. So, whenever we talk about design, please try to understand the requirements of performance and resource usage. That is, performance will be in terms of time, performance will be in terms of maybe power, and the kind of resource, time, memory, power you use. Make it clear that your design will need to consider these aspects. The fourth critical factor for a design is it must implicitly or explicitly satisfy the criteria in the form of artifacts, which mean that you whatever functional specification you can think of, however simple or however complex, a system will never meet exactly those functional specification. It will show lot of other fractured behavior in terms of artifacts in the system. And gone are the days when we used to ignore the artifacts and then later on fall flat on our face, because we did not consider them at the very beginning at the time of design. So, design must implicitly and explicitly consider the criteria that are acceptable for the artifacts. And finally, and last but not the least, is certainly design must satisfy the restriction on the design process itself. In order to achieve the above 4, I do not have infinite manpower, I do not have infinite money, I do not have infinite computing resources, etc., and so on, tools and so on, to realize that. So, design process itself has to work within the limitation, the constraints of the tools, time, cost, human resource, and so on. So, whenever we will talk about design, whenever we will take exercise in design, all these 5 factors, please keep them in mind, because missing one or more of them will certainly lead to a design which will not be workable, acceptable in terms of a working system. Finally, let me close by reminding you that whatever studies you have done so far, you have had a lot of exposure to what is called models. A model is some miniature of a reality. It is not exactly same as reality. A model is certain aspects of a real situation, which is expressed in terms of mathematical form, graphical form, maybe in textual form, and so on. So, we have seen a lot of models in different domains. So, I have just on the left specifically I have kept some school level generic domains, like in physics we have talked about time distance equation. That is, if I know that a train has started moving has been moving at 10 kilometers per second, rather 10 kilometers per minute, and then has been accelerating at a certain rate, then after a given period of time, how much the train will cover, I do not really need to make the train run and measure and find that out. I can make a model of the time distance equation. We typically say S is equal to ut plus half at square or something like this, which will tell me, given the time, the initial velocity, the acceleration, as to how much distance it has traveled. So, that is what is a model, which is not, but it will not tell me what kind of noise the train will produce. It will not tell me whether the travel of the train will be risk free. It will not tell me how much power it will consume in doing this, because this model just models the time and distance aspect. And similar models we have seen in variety of domains that we have already studied, like in chemistry we have seen valency bond structure, which tell us how the different atoms bind to make molecules and bigger molecules and so on. In geography we have learned models of maps, projections, and so on. And if you look into the right hand side in here, these are on the right hand side are some of the engineering applications. Let us talk about electrical circuits. Now, if you want to describe an electrical circuit, you can do it in several different ways. For example, you could just do a schematic diagram. You can say this is an electrical circuit, right? This we say is an electrical circuit. This is a schematic diagram, which this is a schematic of a resistor, this is a schematic of a switch, this is a schematic of a cell, and we can use this by for solving different current voltage equations on this. In a physical reality, if I want to look at this, then physical reality, this resistor will possibly look something like this, where the wires will be connected like in here. The switch possibly will look like something like this, and a cell possibly is like this. So, the schematic is different from the physical model, where you will actually put the cell. If you want to study how the signal will differ based on time, then you will possibly look at the different kinds of time domain signals. So, this is, you will say this is t, this is my signal f, or this is a voltage V that I have at different times. All of these are models, whether it is a time series signal, FFT, a transistor model, we can have static transistor model, we can have dynamic transistor model, we can have interconnect routing. All of these describe electrical circuits, but from various different angles. So, the basic idea of a model is that it makes use of the basic principles that we have been talking of so far. They decompose, they abstract, and they follow the hierarchy. And the strongest element of a model is abstraction. In terms of talking about electrical circuits, all the different examples that I was showing, all of them talk of electrical circuit, but none of them is complete in itself. If I look at the schematic, I do not know really how does the resistor look in physical terms. I do not know how does the resistor behave if a 10 kilohertz signal, sine wave signal is passed through that resistor and so on. I have no idea of those. Whereas, when I am looking at the FFT of the signal, I have no idea of how the interconnection on the breadboard is. So, every model looks at a limited aspect of the system, a limited view of the system, and that is what makes it manageable by the human mind to work with, and that limited view that you focus on primarily gives you the abstraction that you are trying to look at. And in terms of arriving at that abstraction, we can decompose the models further, we can put them in hierarchical terms. We have often drawn electrical drawings, where you will have different subsystems drawn at different levels of details, and as you go deeper into a subsystem, you do more and more detailed models, and at the top level you just have this is the input output of different systems. Similar examples you will find in the building and construction industry, construction engineering as well, that there are different drawings used, plan, elevation, side view. Similarly, on a different model you will have finite element models to actually check out if a strass would stand on its feet. So, models are common in all engineering disciplines, and this is a big advantage, because we all have had lot of experience with dealing with models of variety of kinds. Maybe only thing that is that was missing is we were not repeatedly told that what we are doing is a common activity, cross domain activity of taking concepts and modeling them, solving the problem in the domain of the model and bringing the result back to the real world. That is all that we, but we have been doing this in physics, we have been doing this in chemistry, certainly whole of mathematics is about that. We have been doing this in geography, in electrical engineering, in mechanical engineering, everywhere. So, every model will describe a specific aspect of the system, and this model based approach has a big advantage that once we have a model which is proven, I can build a system, a new model based on this model, because I know this is a proven one. So, this will not fail. So, the resiliency of the system will increase. So, coupled with the approaches of decomposition, abstraction and hierarchy, our next approach in formally going forward in the object oriented analysis and design would be to take a look into the different object models. Here we have talked about decomposition, abstraction and hierarchy in containing the complexity. We have seen that the product of design are models that will help us reason about given structures, make trade offs, particularly when requirements conflict and become a blueprint for implementation. And we will take this forward in terms of actually starting to build models for the complex systems based on the principles we have laid out in the first 5 modules. And our next discussion, couple of modules will focus on how do we make object models and what are the practices to define them and what are the practices to identify and extract them from a real world system.